Today we are going to learn about free fall of a balloon. Let's start with the question, what is free fall? Imagine you are on a tall tower and you drop an object. If there is no air resistance, the object will be in free fall because gravity is the only force making it move downwards. As it falls, it keeps speeding up, getting faster and faster until it meets the ground. This happens because gravity is continuously pulling it and giving it a constant acceleration downwards. So, let's say if the motion of an object when it is falling solely under the influence of gravity with no other forces acting on it, it is called free fall. For example, a ball is dropped from a certain height in vacuum, or an astronaut experience on a space station orbiting Earth, or a balloon dropped from a height. Now, let's consider the case of a balloon. If we drop a balloon in vacuum, a space with no air, it would fall in true free fall, just like an astronaut experience on the space station orbiting Earth. But in reality, there is air resistance. Air resistance usually affects things that fall from a height. It starts to slow down the objects as it falls. There are mainly three forces that affect the free fall of an object in presence of air resistance. The first one is the gravity, which pulls down the object. Second is buoyancy, which push up the object. And the third is air resistance, which slows down the free fall of an object. First, let's discuss about gravitational force or weight. This is the force pulling the balloon downwards to Earth. It depends upon the balloon's mass and acceleration due to gravity, which is 9.8 meter per second on Earth. This force acts constantly and is directed downwards. We can represent gravitational force as Fg is equal to mg, where m is the balloon's mass and g is acceleration due to gravity. Next is buoyant force. Buoyancy is the upward force exerted by a fluid like water or air on an object that is submerged in it. This force is what makes an object feel lighter in water or even float. Buoyancy occurs because of the difference in the pressure at different depths of the fluid. The pressure at the bottom of an object submerged in the water is higher than the pressure at the top. This is the same case in air. In air, the buoyant force is due to the difference in pressure between the top and bottom of the object. This force acts upwards. We can calculate buoyancy as Fb is equal to rho air Bg, where Fb is the buoyant force, rho air is the air density, V is the volume of the object, and G is the acceleration due to gravity. And lastly, air resistance or drag force. This force is exerted by the air as the object falls faster. Air resistance grows strongly and pushes up against the downward pull of gravity. It can be represented in two ways. For lower speeds, drag force is proportional to velocity, which can be represented as F drag is equal to minus kv. And for higher speed, it depends upon the square of velocity, which can be represented as F drag is equal to minus cv square, where both k and c are constants based on shape and surface area of the object. And for calculating the net force, the net force on the balloon is F net is equal to mg minus rho air Vg minus F drag. That is, F net is equal to gravitational force minus buoyant force minus air resistance or drag force. By applying Newton's second law, F is equal to ma, we know that a or acceleration is the first derivative of velocity. We get m dot dv by dt is equal to m rho air vg minus f drag. This equation represents that the resultant motion of the free falling balloon depends upon the relative magnitude of gravitational force, point force, and air resistance. And we have terminal velocity. Terminal velocity is the constant speed that an object reaches when it is falling through a fluid, and the force of air resistance balances out the force of gravity. At this point, the object stops accelerating and continues to fall at a steady rate. So, the condition for terminal velocity is mg is equal to rho air vg plus f drag.